That'll so work.
Yeah.
Take our highest homework grade.
Somebody impersonated the voice and make sure. You will give us 100.
Today in class, he was like, for the bonus, he didn't say what it counts towards. He was just like,
He's like, I'm not
Yo-
sure all of you passed, basically.
he was like, it'll help you, but I don't know how many points it'll give you.
Well, it doesn't
Depends
matter.
on how
We
much you
don't know
put
how
up
many
the
points
final
we
one,
lost, so.
Oh, it's graded after the final.
I don't know.
Or no, he's gonna like release a winner assignment. He's like, oh, you did badly on the final. Here's the review.
So I know you guys are all on break, but you need to review everything.
No, we're boring. Now, so you're like, I'll see you guys on Wednesday. We need to go over this material. You guys did not understand it.
Hey, Mark.
You're all failing.
Whoa.
All right, hopefully you guys did this. His speech was really good today. Like it was very heartfelt. I enjoyed it.
He gave a speech.
Yeah, it was like it was the most dad.
It was
thing
a
ever.
disappointed dad.
Yeah, it was definitely
Oh.
a disappointed dad.
Okay.
Did it.
Gotcha.
One time I missed class. Yep. I got some king shame.
But that's recorded.
He knows. He likes it when other people hear about it.
Yeah.
For the last exam, the recitations that count are gonna be the one you did before Thanksgiving, the one you posted on Thanksgiving, and then this one, and then next week.
I don't think you.
I don't know. He hasn't told me what the material is for the last exam. Is it cumulative or?
No,
Okay.
It starts at the Navier Stokes
Last
stuff,
week?
the,
Mhm.
the time derivative
But he
one.
did it.
Okay.
He
So
posted
that
it. He
should
didn't
be
have it.
2 weeks ago.
2 weeks ago. Okay. So I think, I think Navier Stokes has started 2 weeks ago. So it'd be, this recitation and then the two before. If it's Navier Stokes and forward. Yeah. He also mentioned if you all have like questions, feel free to like come ask him. He said it might be faster answers wise. Even with like the previous recitation where you guys had some questions you were asking me. He mentioned that like it might be faster if you just go talk to him for answers rather than him give me it and then post it on Canvas. And then so anyways, he wanted me to mention that to you if you're wanting a quick answer. What? No, you're good. Okay, so he gave me one problem today. It's a dimensional analysis problem, scaling problem. So he wanted me to work this one through. I think it's pretty good. It's pretty like thorough problem. So okay. So we have a plane scale model. It's a 1/12 scale model. And it's in a wind tunnel. And the wind tunnel has conditions of 20 Celsius and 1 ATM. So standard temperature pressure. And then we know that the model has a chord length. Chord length of the model is 27 centimeters. And which is 0.27 meters. And then we know it has a wing area equal to 0.63 meters squared. And then we have this this table up here for the model of the velocity and force measurements. Yeah. This is drag. Okay. And then what it wants us to find is to estimate the drag on a full scale plane that's flying at 245.87 meters per second. Hey. And at same angle of attack, and at 10,000 meter altitude. All right, so for y'all who just walked in, we have a 1/12 scale model plane, and we have the force, drag, and velocity measurements, wing area, port length, the temperature and pressure of the wind tunnel, and then we're looking for the drag on the full scale model. So, okay. Okay, let me see what I'm going to do here. So what I'm going to do is I'm going to label these rows 1, 2, 3, 4 for easy reference, and I think that might just be helpful, probably. Okay, so if we have a cylinder like so, and then we have like some cross flow that's going over that cylinder, that is very similar to a airfoil of a plane as far as physically goes. The shape's not the same, but the physical scenario is very similar, because it's just a cross flow problem. So when you have cross flow, the two dimensionless parameters that you could use if you're trying to, I guess, describe that situation would be Reynolds number and the drag coefficient. Right, because to do the scaling, what we want to do is figure out some sort of relationship between the dimensionless parameters, and then that'll apply to both the full scale and the scale model because it's dimensionless. So these, in this case, are two parameters that we can use, or two numbers we can use. And he said that if you want more details on that it's in the lecture if you want to look at that. So, or it's in the notes, I guess. Yeah, for this specifically. So, okay, so I think that's all I had to say there. Okay, so we know that Reynolds number is equal to rho v L over mu, and drag coefficient is equal to F over 1/2 rho A B squared. Okay, so yeah, okay. So what we're going to do is we are going to take that table that we have, and we are going to transform it into dimensionless parameters using these. And then we're going to figure out a relationship curve fit. Basically, we're going to curve fit that table of data to get that equation relation. And then that's what we're going to use to then solve the full scale. Okay, so first thing we need to do is figure out at 20 Celsius what is our, because right, this is the wind tunnel condition. Okay, so then what is the density and what's our viscosity that we're seeing in those equations? So density is of air at 20 C is 1.2 kilograms per meter cubed, and viscosity is 1.8. 1.8 times 10 to the negative 5 kilogram meter second. Yeah.
You pulled that from the table, right?
Yes, and he said that that table is going to be provided, right? Yeah. So I think he said in his solution he gave me that like all the tables will be provided to you.
Yeah.
Or I say all the tables. I mean that table and like the
needed table. Yeah. Will be provided. Yeah.
Yeah.
He's been pretty good at tables.
Cool. Okay. Sweet. Sweet. Yeah, and he said it's on Canvas too if you need it for studying or whatnot. So. Okay. So. Yeah, I think that's all I have to say there. So any questions here before I change? Cool. All right. So now what we want to do is for each one of these 1 through 4 runs or data rows, we're going to transform that into Reynolds number and drag coefficient. So I'll say for row 1, okay, we are going to calculate the drag coefficient, which would be, look over here, f over 1/2 rho AB squared. So f is 15, v is 22.35. So here we have 15 newtons over 1/2 1.2 kilogram meter cubed, 0.63 meters squared, and then 22.35 meters per second squared. Cool. So I like to cancel my units just to make sure everything's like, I guess, dimensionally where it needs to be. So I'm going to say Newton is a kilogram meter second squared. So that would cancel. Those all cancel. That cancels. And that cancels. So drag coefficient is going to be 0.0794. No units.
If we're squaring, it wouldn't be meters squared per second squared. So it'd be meters to the 4th over meters cubed.
I think we have, so this meter cube would move up top, right? And would combine with that meter. And so you get meters. Yeah, okay, cool.
Okay.
So, all right, so that's the first one we need. Then we want Reynolds number. So then this is going to be 1.2 kilogram meter cubed times 22.35 meters per second times 0.27 meters. That's like chord length of the wing. So that's our characteristic length is the chord length. And then that is divided by 1.8 times 10 to the negative 5th, our molecular viscosity. Okay, so again, we can say these 3 will cancel that. That cancels that. That cancels that. So this would be 402,300. And again, it's unitless. Okay. So we just do that 3 more times and build our table. So I'll say for 2. And so if it doesn't bother you, I'm going to leave the units off the next 3 since the units work out just the same. But if you want me to do them, just let me know. I'll write it out. But it'll just speed things up a little bit. So drag coefficient this time is going to be looking back at our table, 32 and 33.53. So 32, 1/2, 1.2, 0.63, 22.35 squared. And that's going to give, oh, yeah, you're right. You're right. Thank you for that. 33.53. Yes. Okay. Cool. Thank you. So then that's going to be 0.0753. And then the Reynolds number is going to be 1.2, 33.53, 0.27 divided by 1.8 times 10 to the -5th. And that's going to give 603,540. Then for run 3, we have 44.7 and 53. So then I'll say for 3, we'll have okay, 53, 1/2, 1.2, 0.63, 44.70 squared. That's going to give 0.0702 Reynolds number, 1.2, 44.7, 0.27 over 1.8 times 10 -5th. 804,600. Okay.
We'll just go back to the last slide just for a second.
Yeah, sure.
So if you're doing so if we're doing this on any homework or whatever, do you think we have to check to make sure the units cancel every time if we want it to be unitless, or can we just assume it'll be unitless? Like, do I have to go through and make sure it cancels?
I mean, you can assume it does, but there's always the risk of if you do make a mistake in there, I've done things before where maybe I had kilonewtons, and so then I was off by a factor of 1,000 because I didn't put the units in there. So there's just always a risk of something might be scaled wrong, yeah, of course.
The drag coefficient should be a pretty small number in general when you're calculating it, or be pretty.
Oh no. I didn't even touch anything. Oh, we got it. Yeah.
Is it it's typically a smaller number like that, a lot bigger, or depends on what you're.
I mean, it's going to depend on your scenario, right? Like the shape and whatnot they're using. But if we look at this,
Yeah, I mean, the more force you apply, should gradually shift it.
Right. You're defined by the square of the velocity.
Yeah, but also
So,
velocity factor.
yeah. So, I mean, if you have like maybe a really, really slow flow, then, but then your force would be less too. So I guess it really depends on the data that's provided. I would think it'd be small, just looking at the way the numbers kind of work there. So I would think it would be small, but it's going to depend on whatever shape and data you get. So, but then for your Reynolds number, in the case of like a plane, that's like super turbulent, right? So you kind of expect that you're going to have a high Reynolds number. Yeah. If it was like some sort of laminar scenario, which I don't know if you would have a laminar scenario, but it'd be a lower Reynolds number.
Yeah.
So
That's why I was like, I didn't know if there was kind of a scale like that with Reynolds number, where it's like you kind of know what direction it's going versus like with drag coefficient.
Yeah, I mean, I guess with drag coefficient, I don't really have a good frame of reference for what like kind of an upper limit would be that he could do. At least in this problem, the trend is they're all small. So. All right. So then for number 4, we have okay. For number 4, we have 55.88 and 80. So this is going to be 80. And that'll give 0.0678. And then the Reynolds number is 1.2, 55.88, and 0.27. And that's going to give 1,005,000. Now you're good. It would be really funny if this just like cut out whenever that happened. It's just like me like touching it has no effect, but then like random stuff knocks it out. Okay, so all right, those are our values that we're gonna work with. Okay, so we can write those down into a modified table. So what we're gonna do is we're gonna transform velocity into Reynolds number and force into drag coefficient, right? Which kind of makes intuitive sense that those would be related. So here we're gonna have Reynolds number, drag coefficient. And so I'm gonna write these values down here. 402, 300, 603, 540, 804, 600, and 1,005,840. And the drag coefficients are like so. All right. So then what we can do is transform this into a log-log scale to make this more linearized. Linearized. I don't know how you say that. I guess that's how you say that. But so we can rewrite this as log of Reynolds number versus the log of the drag coefficient. And so that's going to give us 5.605. And also, just a note, this log is base 10, right? So that'll be useful for later. And then 5.781, 5.906, and 6.003. And then on the other side, we have negative 1.100, negative 1.123, 54. Okay. Any questions there before I move on to the next?
What's the motivation for doing this again? For taking a lot of those sides?
Numbers are easier.
So if you were to graph this, you would end up with like some sort of thing like that. So then the equation would be some sort of exponential. When you take the log, you end up with linearized. Yeah. Yeah. Because the scale here is going to go, how's this? Let's see, I guess it's like, you get these gradients like 1, 10, 100, 1,000, you know what I mean? And so then, yeah, so it ends up like making it a little easier to look at. So, okay. So, okay, so that data, I plotted it in Excel. There it is. So, drag. Do what?
Big Excel.
We got the Excel.
Big Excel.
Oh, there you go. Yeah, this is like the most basic chart I probably could have done in Excel. But so drag coefficient, log scale is on the y-axis. Reynolds number log scale is on the x. So this is that's that. This is log of, okay. And we have our equation right there. So yeah. So that's our thing we want right there. This?
Yeah, how will we plot that?
It's the only question.
I mean, I'm assuming is he gonna let you have like a computer? I'm assuming not, right?
No.
Just, I mean,
If
I
he
would,
is, this
yeah.
is gonna be a good example.
I mean, I mean, I wouldn't think that he would have you like, do that.
Yeah.
Or maybe if he did, it would just be like a really easy numbers. Like you could do like a point slope form, maybe.
Okay.
But he honestly hasn't told me. I doubt he's gonna make you plot like a computer type thing.
Or you
So-
just give the equation.
I wouldn't think he's gonna make. Yeah, basically, I don't think he's gonna make you use
I
Excel.
prefer the computer.
I wouldn't think.
That's
You do?
You should suggest to him. You should suggest to him that we can use our computers for
It's gonna make the questions so much more. Yeah, if you
Yeah.
finish your computer, the question.
Yeah, it's not like I'm
He
answering.
already.
minutes.
It's like when you have a one question take home.
Is it one
We're
line?
gonna talk about.
We mean ChatGPT Scholar can't do it.
Yeah. With regard to that, I would just ask him about how he might handle that type of thing in the exam, because he hasn't told me anything about what you're allowed to have or what he's planning. So,
I mean, you've got.
yeah.
Yeah.
If you have an Inspire or an 84, maybe. Something like that.
The Inspire's great.
Yeah, it is.
What if you have a Lenovo?
A Lenovo?
Yes, like the school issue ones.
I mean, oh. I mean, you got MATLAB on there. It's pretty powerful. Although MATLAB will not do that log by default, so it could. You can do it, but he mentioned to me today, because I was asking him, like, do I plot in MATLAB or Excel? Like, well, I said MATLAB. He was like, I would do Excel because MATLAB uses natural logs the default. Anyway, that's a tangent, but
Well, I wrote your name in when I voted for president, so.
Oh, man.
thanks. Got one vote. That's good. That's more than I thought I was going to get. So
That's
that's
new,
good.
actually.
Oh, okay, okay. On the resume.
Just walk into the fluids room at the beginning of like the lecture next time, 4 years from now, be like, hey, remember to vote for president. Really appreciate it.
All right. Okay, so we have that equation. So recap, that equation is the relationship between the dimensionless parameters that we derived from the data of the scale model. Because it's dimensionless, that will apply to both. Oh no. There we go. So that will be true for both. So that's kind of how we're bridging the gap here. Okay. So now for the full scale step. Okay. Okay, so at 10,000 meters, you're going to use the table I'm about to show you, which will be provided. I'm assuming that they'll both be, I mean, he's specifically mentioned this one. I'm assuming the other standard properties, will be provided to you as well. But he just gave me the values for this. But for this table, he did provide it in his solution, and it's right there. So we want 10,000 meters. So we know our density is 0.4125, and our temperature is 223.16. We need that value, and that value. So we have alrighty. So that's the data that we need. And then, okay, so then what we need to figure out is what is the viscosity? So he uses this relationship that he said he gave to you in class. It is to the n. Okay.
So you need that end.
Yes. Yeah. Okay. So then, okay. So we're going to plug some values in there. Then our new viscosity, our old viscosity at room temp is this guy. Okay. And then temperature is at 223.15 Kelvin over 293 Kelvin. And our N in this case is 0.67. That is based on the fluid, in this case air. Okay. And there's a table that comes from. So okay, so then if we go ahead and calculate that, that's going to give us our viscosity equal to 1.49 10 to the negative fifth kilogram per meter second. Okay. So then we also need to know what's our chord length. I'm going to do this. Okay. So now, what's our chord length full scale? So I'm going to call this LC full. And it is going to be equal to 12 times the previous chord length, which is 3.24 meters, since it's a 1/12 scale. Okay. So now we can go ahead and calculate our full Reynolds number, which is going to be the new density we're working with times the speed of the full scale. Is that right? No, 87. And then the chord length we just got. And then that's divided by our new viscosity. And that is going to be equal to it got super turbulent just now. A lot more than it was. 043.96.
Yeah, that's around what I was estimating.
I was gonna maybe ask you to guess if you want to. You probably would have been right on. You might have had more decimal points out, you know.
The classic 22,054,000.
The characteristic 22 million Reynolds number.
I'm also trying to figure out like what plane it is based off the weird chord length
Yeah, I don't know.
for 112. Like that's pretty small for chord length.
For
For 3.24 meters.
I mean, that's like a 10-foot wing.
That's pretty small.
That's pretty small? Really?
For like a chord length is across, right? From like edge to tip.
From leading edge to trailing edge. Yeah, yeah. Chord length is, if you look at the airfoil, it's this length.
Yeah,
I think
so
it's-
it's like the length of the wing of like a singular length.
Well, it's not the,
Or is it
if this is the plane, it's not that.
okay.
Yeah, it's this cross section depth.
Gosh, that
From
makes sense.
Yeah, that's of course. So it's like like if you like laid down on the wing,
Yeah.
and the wind was like blowing in your face, you know, you're like it's that direction. You like that one? If you're like Tom Cruise, you're like hanging on. Yeah, you are chord length. Okay, so it just occurred to me that depending on what movie it is, Tom Cruise is either in the plane or hanging onto the outside of the plane. That just randomly popped in my head when I said that. Okay, so we have 22 million Reynolds number, really high, very turbulent. Again, unitless. So then now we use our equation. So, right, I'm going to change pages. So our equation is, if we go back here, this y equals, that thing. Y is log CD, and x is log Reynolds number. So we can write that as log CD equals to negative 0.1787 multiplied by log of Reynolds number. Yes, and then minus 0.0959. Okay. And then this is where I was saying, note that there's a base 10 there, because what we're going to do is raise both sides to the power of 10. Well, yeah, to a base, I guess raise 10 to that. However you want to say that. 10 is the base there of our exponent. And then this will give CD equals to 10 with an exponent log. I'm going to go ahead and plug in that Reynolds number that we just solved for. 4396 minus 0.0959. Okay. And so that whole thing is going to give you a drag coefficient of 0.0391. Okay. So it's still really small, just kind of connecting that there. It's actually even smaller, I think, than it was. What was it before? Yeah, so it's like half, I guess, of what it was. Okay. So what were we looking for? We want to know the force of the drag, right? So last step here is, so want force of the drag. So we can say that we know that CD is, again, from before, F over 1/2 rho A B squared, which we can write as 0.0391 is equal to F divided by 1/2. This is the full scale density of air, kilogram meter cubed. Then we have this value multiplied by 12 squared. And then we have 245.87 meters per second squared. So this 12 squared here, just to give you a kind of a visual, airfoil, right? We have the cross flow, like we're talking about. So our leading edge is that edge there. That's the leading edge. So if we think about the plane, kind of like I drew it earlier, where we have a wing coming out to the side like that. Yeah, something like that. That area is kind of like this. It's this area, sort of, if that makes sense. It's that area. So, you know, before our area was 0.63. And so now we have to multiply both of those sides by 12 to scale up to the new plane, or to the full scale plane. Okay, so yeah, I actually realized I have a number wrong in here, so I'm gonna replug this into my calculator to make sure that I am giving the correct value. But yeah, I mean that's basically the whole problem. So yeah. Okay, let's see. So 0. All right. And what you get is F is equal to 44,226.731 newtons. You guessed it, right? Probably.
I was just thinking 2 in the middle relates to the 22 million. So that's how I guessed it.
Oh, okay. I didn't put that one together. That's good. Good. So, anyways, so that is the drag on full scale plane at 10,000 meter altitude at 245.87 meters per second. Any questions about that?
Can you elaborate on that, like 12 square thing?
Yeah. So, okay. Right. So the plane that we had before was had a wing, right? And the area that is impacting the drag is kind of like this cross-sectional area here. Right. And so for the scale model, that was 0.63 meters squared. So when we do the scaling, we're doing a length scale.
So it would be scaling it, the length by 12 and then essentially the height in this case by 12.
Exactly. Yeah. So each of these is going to multiply by 12. And so then the area full scale is 12 times 12 times. Well, yeah. Does that answer your question?
Yeah.
Cool. Sweet. Yeah. All right. Well, that's all I have, unless y'all have like questions or yeah.
So for most of the problems we've done in class on dimensional analysis, we've had to find the unitless parameters that define like the situation.
Mhm.
How did you know that we didn't have to find them for this one? That we just use Reynolds number and coefficient that?
He just gave me those.
Okay.
Yeah. Yeah. So he also explained to me like a situation where you could do like a pump, and you could define like a dimensionless power variable and like a rotation speed variable, and so there were like 4 different ones or 3 different ones he used. Yeah, so he didn't specifically go over how to get to which ones you'd use, but I think he mentioned he gave you like he's going to give you homework that will have, I guess, more of this type of thing on there.
Yeah, the number that we have, it's just like 7 parameters. And
Okay.
we have to find the 4 unitless variables and define it.
Okay.
I was actually gonna ask you about that too. I know when we're using like the pi theorem,
Mhm.
that we have like repeating variables, like there's 3 repeating and then 1 is, just utilizes the rest of the remaining variables.
Okay.
How do we determine the best repeating variables to use? Because I know in class he said that you want to choose it so that the dimensions of the repeating variables don't cancel out completely. So that way when you add the 4th variable, it does. But I was trying the homework earlier today and I cannot figure out the right ones to use.
Okay. Well, I don't know. Yeah,
Fair enough.
that's the best answer. So I can, let me make sure I'm understanding that correctly. So if I'm being honest, Buckingham pi theorem was like probably one of my most confused areas of fluids when I took fluids. But yeah, you're welcome. So asking him is probably gonna be the best answer. But you're wanting to know, how do you know which 3 to pick
Yeah.
to best represent?
'Cause, like I was
okay.
doing multiple iterations and I tried different things and I got like different answers for all of them. So I'm like, okay, how do I know which one of these is the right answer? 'Cause
Okay,
there's a
okay.
bunch of different ways.
Okay. So you're basically saying, how do you pick the 3 to optimize the 4th? Or how do you pick, like, how do you know which 3 to pick?
Yeah, that like stay in every single like pi variable.
Okay.
Yeah.
So,
I asked him today and he kind of elaborated, but I tried to imply what he said to the homework and it did not.
okay.
So we had a 30.
But if we all do 35,
And so you're saying that depending on which order you picked in, you kept getting different answers?
Yeah.
Okay, and they were like significantly different? Or were they just like a little bit? Pretty different, okay. I'll say, you had 4, right, you said, total?
Yeah, like there's 4 total pi variables, each with 4 terms, and I want to know how to pick the 3 terms that repeat in every one of those pi variables.
Okay. So 4 pi variables with 4 terms each. How to pick 3 repeating terms.
I was
Yeah.
listening to the lecture, and the only thing he said is that he said it requires like good knowledge of like what's happening, and that you want to. Yeah.
oh, I'm done for.
This is
How do you
how-
know, guys?
And then you want to pick them so that the units don't, like if I pick smart, like if I did something like, density, I would want to make sure I don't pick another variable that like could eliminate that term. Because if I have those 3 repeating variables, if I do dimensional analysis on that and there's a possible combination where I can eliminate all those terms, then when I plug in the 4th, it's not going to be human computer.
It sort of sounds like he's talking like about like dependency on each other. Like you might have some terms that are I guess linked to other terms. And so then if like you like modify one of those, dimensionless quantities, then you're going to end up modifying the other ones too. So maybe you have to pick them in some way to where you're not going to,
Yeah, how does
it's like kind of sounds like.
It's a backdoor way of like how he's like referenced when he went over like the omega in class. Was it like, it was angular velocity and then like multiplying it by a dimension to like manipulate it a certain way. You get the same thing and then you come to like Reynolds number by some backdoor way.
Honestly, that's the part I get. That made sense to me. It's like literally, because that's just once you have the 4 like pi or however many pi variables you have, once you have them, I can find them like that. I just don't know how to write the expressions for those variables correctly.
Yeah, it sounds like maybe there's a dependency thing going on where they're, they're related, but for, he'll be able to explain it way better than I can, of course, because don't know a whole lot about that, but yeah. But anyways, I'll put it on there. I'll try and ask him myself, but if you don't hear an answer back from me, like if I can't get a hold of him or something, then he's got office hours. So okay, cool. Yeah.
Are you gonna have another one next Tuesday? Is he gonna be like
I assume so.
is he gonna be the practice exam, you think? If he
Probably. You only ask him to not if he could do something else, or do you want the press exam?
I feel like I want both.
Both? Yeah.
Both would practice
2 hours.
Yeah. 2 hours inside.
You want all your time. Meeting on Tuesday, and then I also did a meeting on Wednesday. I could just ask you a question versus another practice. Maybe that if you have time.
Yeah, he's got.
Maybe. Yeah. I've got nothing going on. I mean, I can ask him what his plan is there.
Extra is always nice, but
Yeah. I'm sure he'll do a practice exam regardless, I would think.
yeah.
But I can ask him about maybe doing some problems that are separate, so you have like two sets of, and then that way you'll have solutions to the practice exam.
I'm not practicing, I know that I failed.
The same as the practice exam, but if you change the question.
Right. Exactly. Yeah. See extra problems. Yeah, ask him about that. Sure.
I mean, if you just want to, eat a simple fish
Get him off block.
Poor guy. Apparently I was wrong. Apparently Brett doesn't.
No bar?
5 minutes to get my ass
What?
over that.
No bar?
So, I'll see you guys.
bowl.
I have my mini fridge.
You want to pop up? I think we're just doing an exam review.
I gotta go.
That was like an hour-long problem.
That was insane. You're like, yeah, that's it. I'm like, you just spent like 4 or 5 pages on that. I'm like, that's,
Well,
that's 1 in 5 questions. How long did you spend on this one prepping it before?
probably 2 hours, 3 hours, something like that.
So it's a fair exam question. You'll get it done in an hour.
I don't know about that. I'm not sure.
Speed run. It's like thesis.
Speed
We're just
run.
have 1 question finals. Dude.
Whew, that would be rough.
I don't think it's that bad. I was looking at it. It's just, did you take modeling analysis or did you take differential equations? I took DPQ. That's why. Modeling analysis did those exact same questions.
that.
Thesis.
Oh, crap.
I like,
Is that there? Okay, okay.
yeah, it's making math. Just see it that
Is
way.
it
I think so.
Or is it, where's it kind of?
Uh,
Oh.
Yeah, no problem. Y'all have a good one. Yeah.
I know you have a question. He's having us like redo the final or the exam. For this one, I was having trouble finding P1 since he doesn't give it in. He doesn't give P1. He just gives it as P1. So, am I supposed to use Reynolds or Bernoulli's equation in order to find P1 for that? He gives the. Or, I'll show you the question.
Yeah. I haven't actually looked at this at all yet.
Okay.
I would assume Bernoulli's. Yeah.
Bernoulli's.
I would assume Bernoulli's.
So wow, why can we use Bernoulli's on this?
Why can you use Bernoulli's?
I understand that it's. I know that he said like the 4 cases is like it has to be laminar flow, frictionless and whatever. But if am I using what am I using for my P1 and for my P2 then in that case? Or am I using that one or am I using the V squared over 2 whatever the thing is?
Yeah, so Bernoulli's you wouldn't have any height effects. You'd assume that's 0, right?
Yeah.
And then you'd have a velocity change,
Mhm.
V over 2G. And then you'd have the pressure effect.
Mhm.
Do you know your velocity
Yeah.
in there? Okay.
He's
And you know P2?
P2, yes. P2 is atmospheric pressure.
Okay. And then he gives you no sort of gauge pressure.
No.
Okay. Okay. Yes, if you know P2 is atmospheric and you assume the Z effects are 0,
Yeah.
then I would think you use Bernoulli's.
Okay.
And it says then you know your velocities, you know P2.
So then I would use okay, so then I would use the first two terms of the Bernoulli's equation for the solving for P1.
I think so. Yeah. Yeah. So you have like trying to remember what it is. It's P1 over rho G,
Yeah.
maybe, and then plus V squared over 2G equals, and plus Z equals same thing.
Yeah.
So then Z's would be 0, or like cancel, I guess, same height. And then the P term on the right hand side would be 0 because of atmospheric.
Oh, really? So,
Right.
oh, because we're treating it like gauge pressure.
Right. Well, yeah, you treat it like P2 is, if you treat both as gauge pressures, then P2 would be 0. And then whatever you find for P1, that is a gauge pressure because it's going to be measured against atmospheric.
Okay.
Yeah.
So then it will be P1 minus the atmospheric pressure, which he gives. And then,
Well, usually when you solve, like if you have a boundary, and so you have pressure acting inward on it, right? You want to use gauge pressure there because if you use absolute pressure, then you would have to account for the atmospheric pressure applying to like the whole body.
okay.
You know what I mean? And so then you'd have like this weird area. If you have like a big like that nozzle,
Yeah.
you'd have like this weird conical area that the atmospheric pressure's on. So that's why you want to use gauge pressure. That way it sort of takes out that complexity.
Okay.
Yes.
So to do P1 minus the atmospheric pressure divided by rho G, and then I have the velocity term, and then the velocity term for the second one.
Yes. Is there a marker? Yeah. So just from looking at it quickly, this is what would make sense to me. But because I would think Bernoulli's would apply here. So this is just my preliminary analysis. What would make sense to me? Those cancel.
Yeah.
So this working with gauge pressure, that'll go to 0. Then you know this, you know that. You know gravity, right? And so then this is a gauge pressure. But then you want it to be a gauge pressure, I would think, because when you start solving like P1 times A1, you want that to be a gauge pressure. And because it'll simplify the calculations. Yeah. So that's what I would think. And then you just subtract that over and multiply by rho G. And I think that's how I would approach solving for P1. Yeah.
And the density for the P1 would be the density of the water, not the atmosphere.
Right. Yeah. Yeah. Because I'm assuming this is a nozzle.
Yeah.
Right. And we have some sort of reduction in cross section. So what I'm thinking is that, you have like a hose, let's say. Well, I'm not exactly sure how he's worded this. I guess this is atmosphere out here.
Yeah,
Is that right?
That's what he said. Yeah.
So so this is all water, right? So then right here, there's a solid boundary. You know what I mean? So like the atmosphere, there's no air in here, right? So this density would be water density.
Okay.
And even right here, where you have the water exiting,
Would you keep it water density or would you do the atmospheric density?
it'd be water.
Water.
Yeah, because what you're analyzing with Bernoulli is you're analyzing the streamlines of water, right, that are flowing.
Yeah.
So, yeah, it would be water density, and then the atmospheric. I think the only implication of that is just saying that the pressure here, which is of the water, is just relative to atmospheric pressure.
Okay.
So, but as far as like the fact that there technically is air out here, that doesn't come into play anywhere. I don't think.
Okay.
Yeah.
And then,
Excuse me.
yeah, for
There's just a growing collection of water bottles over here of people who've left stuff.
it's insane.
Yeah.
People must get real thirsty.
Oh yeah, exactly. If I lost my water bottle, I'd be looking everywhere for it.
I mean, it seems like you have a growing collection of stickers and stuff.
I do, exactly. It's like irreplaceable. Yeah.
So I was trying to resolve this one, number 3,
Mhm.
and I got lost at, what was I doing? Subtracting. Oh, so for this one, do I choose for the buoyancy force? Do I choose the density of the air in order to do that?